nomenclature where the alkanes are named as saturated hydrocarbons by adding the suffix ANE. We add that suffix on the stem name, and the stem name is got from the number of carbon atoms.
Okay, that's good.
Then we talked about the isomerism, that the structure isomerism. Then we talked about the preparation.
Preparation of alkanes.
We talked about preparation from unsaturated hydrocarbons. We started with using an unsaturated hydrocarbons. We reduce like alkanes or alkanes, or we reduce alkanes or alkali to get our alkanes. Then we use the catalysts like nickel. When you use nickel, you apply heat up to 150.
That's good.
Then when you use platinum and palladium, the reaction takes place at room temperature.
Yeah, that is good. So that is one method, and then which other method did we talk about?
Then we again talked about the from halogen
Okay.
we said that the
Alkyl halides.
alkali halides are reduced by zinc in presence of concentrated. Yes,
Acid.
they are reduced by zinc in presence of hydrochloric acid.
Yeah, conc HCl. Yeah.
And then we get our alkanes.
Yeah, that is good. Then another one.
Then we again talked about the Waals reaction.
And with Waals reaction, what did we talk about?
That the other, I still remember that it was reaction, the carbon atoms reacting double.
Yeah.
Like when we have like two carbon atoms in the reactant, we get 4.
We get 4. Yeah, that is good. So there is doubling in other words. So yeah, thanks for that lesson review.
Yeah.
Okay. Yeah, thanks for that lesson review.
Yeah.
It shows that you are really doing some good work. Okay. And please keep it up.
Yeah.
Please keep it up. So right from where we stopped in the other lesson, that's where we're going to begin. Still on preparation of alkanes, we can prepare our alkanes from alkyl halides, right? You can prepare from your home. We can still prepare alkanes from alkyl halides, right? And like I told you, alkyl halides, you have an alkyl group, which is usually represented as R, and then a halogen. So if we react these alkyl halides with zinc and copper, you get a mixture of zinc and copper. Okay, you mix them together, and then you need an organic solvent such as ethanol, then we shall form an alkane. Okay, whereby the zinc is going to take away the halogen and then you remain with an alkane. So this reaction is also equally important, and you can have that the alkyl halide, you can see. So now when you're given such, we don't mind about the ring, and you shall study benzene and you shall see. So we don't mind about the ring, okay, but rather this aliphatic group. So this one behaves as an aliphatic organic compound, and you react it with zinc in presence of copper. So the zinc mixed with copper, we form that zinc copper couple. Okay, it's a couple, they occur in pairs in presence of ethanol, then we shall form an alkane. Okay, and this is the alkane of ours. So I hope that one is good. Maybe I can give you some simple, but this is just simple work. I know it is simple. It is just simple work. Now you have CH3, CH2. Maybe I can put the C here, and then I put the C here, CH, and then CH. This is CH, and then let me put the BR here. Okay, and I react this. So what will be your product? In presence of zinc, copper couple, okay, and ethanol. So what is your product? So the product, you can just say the name.
I think the answer is butane.
Yes, you think the answer is butane. Somebody joined? Who joined?
Me.
So CH3.
Tim.
Who joined?
Tim.
So 1, 2, 3, 4. Yeah, this is a 3. So our answer is going to be butane. As simple as that. Yeah, so basically that is how we can prepare alkanes using zinc, copper, couple. Now these reactions, like I told you, and I always say this, organic chemistry, once you know preparation, this is a magic bullet. Okay, and then after knowing preparation, reactions and reaction mechanisms, this is also another magic bullet, because all questions rotate. This one, it will help you answer synthesis questions, where they say synthesize this from this, synthesize this A from B. In this one, it will help you to answer the reactions and then mechanisms. They will give you equations, and they say write the possible mechanisms or complete the equation below and suggest the possible mechanism. So those are the two magic bullets. If you fail to use them, then you become doomed. So let's talk about this reaction. Now, before I display this reaction, let me talk about the importance of this reaction. This reaction is so important in organic chemistry, in organic synthesis. Okay? especially in reactions that involve reduction of the carbon chain. For instance, you may have a compound that is made up of 4 carbon atoms, but they want you to synthesize a compound that has 3. This reaction is equally important. This reaction is important, okay, in reducing the carbon chain. Now you should be insinuated. You should be asking yourself that which reaction is that, and how is the reaction done. So feel free. Here is the reaction. Now we can prepare alkanes, okay, from carboxylic acids or carboxylic acid salts. Now, what are carboxylic acids? If you remember our very first introductory lesson, we said that if you have this group, you have O here, okay, and then you have the OH. If you have this group, okay, for example, you can be CH3, COO, then H. Now this one is a carboxylic acid and it is ethanoic acid. So if we can remove this, the whole of this group, and we form an alkane. Should I repeat? We can take away the whole of this group and we form an alkane. So alkanes can be prepared from carboxylic acids or carboxylic acid salts. And how do we prepare alkanes from carboxylic acids? We react a carboxylic acid with a fused sodium hydroxide, not a solution, but fused sodium hydroxide, or you can say soda lime. Now, what is soda lime? It is a mixture of calcium oxide, this is a salt, sorry, this is a solid, and then sodium hydroxide. So when you mix the two, you get soda lime or fused sodium hydroxide. So when you react this fused sodium hydroxide with a carboxylic acid, then you produce an alkane. But a good thing here is, for example, you might have CH3, okay, COOH, okay, and you react it with fused sodium hydroxide. You can say sodium hydroxide in presence of calcium oxide. Oh, this one, it is a mistake, the keyboard, my touchpad sometimes misbehave, that you may think it's a 2. No, it's not a 2. So we shall form our alkane. Now the reaction proceeds with a reduction in the carbon chain. Does it make sense to you? The reaction proceeds with a reduction in the carbon chain. Okay? That's brilliant. Let's look at some reactions. For example, you may have CH3, then CH2, then this is your carboxylic acid. And then you heat the mixture with fused calcium, with fused sodium hydroxide, or fused soda lime. We shall form, and then when you heat it, then we shall form our alkane. And then sodium carbonate plus the water. So this reaction is important. Why? Because see, this one has 3 carbon atoms and this one has 2 carbon atoms. So for instance, I might give you this. Show how you can prepare ethane. Okay, that's too much. Prepare this, you effect this reaction. However, I might not do it now. Okay, this is CH3, sorry, CH2, and then Cl. And I want you to prepare for me just this. CH, CH3, and I want you to prepare for me just this. So do you see? Now, because this one, it has 2 carbon atoms, and this one has how many? Has 3. Then you should, in your mind, you should find ways, we should find a way of reducing the carbon chain. Okay? And one of the ways is this, whereby we shall find ways of converting this into a carboxylic acid, and then from that carboxylic acid we react it with fused sodium hydroxide. Okay, then we shall take away the carboxyl group and we produce an alkane. Okay, yes, so we shall find ways, and in this case I can produce this. I won't write for you the reagents now, okay, because we haven't studied these reactions with CH3, and so I can form this OH. Okay, after all, this is a primary alcohol, and then from OH, yeah, we have done this reaction. I'll write it. Then from this I can produce my carboxylic acid. We haven't studied this and haven't seen it anywhere, so I won't write it. So I produce my carboxylic acid, and then from my carboxylic acid I can produce an alkane. So whereby here here we shall heat this with sodium hydroxide solution, not fused, but just sodium hydroxide solution. Okay, and then we do the heating. Now there it will undergo what we call nucleophilic substitution reaction. You remember those reactions we studied? Yes. So here it will undergo nucleophilic substitution reaction, where this sodium hydroxide, it will give us the OH ions that will displace the chloride ions. Okay, that will displace this, and you form an alcohol. So this is a nucleophilic substitution reaction. And then after forming this, then we shall oxidize our alcohol. But I want to anyway let me write it. So here we shall use potassium manganate, any oxidizing agent. You can use potassium permanganate, you can use potassium dichromate 6, but it should be acidified. So here I can use potassium manganate, okay, 7, but it must be acidified, okay, and then I do some heating, okay, and I do some heating. So if this, then we shall form a carboxyl or carboxylic acid. And then from our carboxylic acid, then I shall react it with fused sodium hydroxide. Sodium hydroxide, okay, in presence of calcium oxide, and then I do some heating, okay, and then I shall form this. So this is what we call synthesis. Now, there is no lesson where they will teach you how to synthesize, okay, but as we are studying, then we talk about this. And for instance, today I've talked about synthesis, so I've introduced synthesis. So that's how we synthesize. Okay, you look at what you have and then what you need and see how you can connect them. So do you see how this is important? How important this reaction is? Yes. Yes, somebody has joined. So basically that's how you can prepare alkanes from carboxylic acid. Let's see how we can prepare our alkanes from carbonyl compounds. Now, what are carbonyl compounds? Like I told you in our first lesson, that one I gave you the course outline. If you have such a compound, and if you remember in biology, if you have carbon and the carbon has oxygen, okay, now this side and this side, the carbon is bonded to either hydrogen, and then this side the carbon is bonded to a carboxyl, an alkyl group, or the carbon has oxygen and the carbon this side is bonded to an alkyl group, and also this side bonded to an alkyl group. So if you have such a compound, then that compound is a carbonyl compound. And this one is an aldehyde, and then this one is a ketone. Okay? Yes, that's good. That is good. Now, we can prepare alkanes from carbonyl compounds. Okay? If we reduce this group, this carbonyl group, and we take it away, and then we add their hydrogen atoms on this carbonyl carbon. And how shall we do it? If we heat this, okay? If we heat this carbonyl compound in presence of zinc and mercury, okay? Okay? Or you can call it amalgamated zinc, okay? But this reaction is going to occur in presence of conc HCl. Then we shall form our carbonyl compound. So we shall form our alkane. Let's see if I have a reaction, and I think I do. I do have it. So you have your carbonyl compound, okay, which is ethanol, or it could be a ketone, okay, and you heat this with amalgamated zinc, mercury, and zinc in presence of conc HCl. Then we shall form our alkane. So aldehydes and ketones, that they do contain oxygen atom on the carbonyl carbon, it is this one. It is going to be removed by zinc, and then you donate.
Teacher, please pardon.
Why, pardon? It's okay. So I was saying, it's okay, you can mute. So I was saying that we can prepare alkanes from carbonyl compounds, okay? And I was like, carbonyl compounds, they are compounds that have a carbonyl carbon, you have oxygen there, and oxygen is either bonded to hydrogen this side and an alkyl group this side, or you have carbon and the carbon is bonded to oxygen and you are either bonded to an alkyl group this side and another alkyl group. So this one becomes an aldehyde, okay, this is an aldehyde, and then this one is a ketone, okay. We can call it as depending on the number of carbon atoms. So we can prepare alkanes from these two, okay. And how we're going to prepare, if you find ways of taking off,
Excuse me, sir.
yes, Edwin.
Why does that R has an exponent and the other one doesn't have?
It's okay. There now, the reason why I put this one, it is to show that they are different. This is not the same as this. this alkyl group, it can be CH3, it can be a methyl group, it can be an ethyl group, okay? It can be a propyl group, and so on, okay? And so on, and so on. It can be so, and so on. So this R, I just put this to show that they are different. This R is different from this R, okay? Yeah, but in other words, this one can be a methyl group and this one can be an ethyl group, and that is still a ketone. But there is no science, there is no chemistry, okay? Yeah, this is just convention. Yeah, that's good. So this one is a ketone, and then this one is an aldehyde. Okay? Now, if you find ways of removing this oxygen, find ways of knocking off this oxygen, and then you hydrogenate it, you add there hydrogen atoms, then we shall form an alkane. Okay? We shall form an alkane. And so if you react this with zinc in presence of amalgamated zinc, okay? Okay? Zinc with mercury in presence of Kong HCl. Now, like I told you, these organic reactions, they are too slow, okay? That they require catalysts to proceed. So this reaction, it occurs slowly. So when you add there amalgamated zinc and conc HCl, then you will attain the products. The products are going to be formed. And in this case, our product is going to be an alkane. Okay? Yes. So I hope I have some reaction here. Yeah, so this is ethanol. Why ethanol? Because it has carbon 1 and carbon 2. Okay? And why null? Aldehydes are named by adding Al. Okay? They are named by adding Al on the stem name. So this is ethanol, reacted with zinc, or amalgamated zinc in presence of conc HCl. Then we shall form an alkane, and in this case, it is ethane. Is that okay? Everyone? Anita, is it okay?
No.
What is confusing?
That part of Simanyanga alkalides.
The alkyl, the carbonyl compounds,
The haldides and the ketones, that part.
No, we shall study them. I was just giving you a hint. But that is a functional group on its own, and we shall study, okay? Carbonyl compounds. But I was just giving you a hint to show you what they are. So you can see, whenever you have, let me get some. So whenever you have oxygen directly bonded to carbon, like this, and this side is either H or an alkyl group, CH something, then that one becomes a carbonyl compound, and there are two. We have aldehydes, and this one is an aldehyde, and then ketones. Okay? Yes. So it shouldn't bother you, it shouldn't worry you a lot, okay? We shall study them, and we shall see what they are, their chemistry and stuff like that. Not so? Yes. So let's see Oh, you have that question? You have this simple question? Can somebody give it a shot?
So first, give me the name. The
First,
previous slide.
it's okay, have no worries. Are you done with the previous slide?
Yes.
So, can you give it a shot? We have some simple question here, just to introduce you to synthesis.
In the chat box.
You cannot write a synthesis question in the chat box. It becomes hectic. Just write just write on the paper, okay? And then I shall do it from here as you are marking, as you are going through what you have written. Okay, so we have this simple work. We have this simple work, and the work says complete the following equations. Oh, yellow in yellow, and this CH3 is here. It is here. It was just an error, but this CH3 is attached here. What's your product? Don't drop it in the chat box, but you unmute and speak. And then we also have this. What is your product? And all of you must speak. This is 1. You say 1, the product is this. And you say 2, the product is this. Who has finished? Let's hurry up. No one? Yeah, thanks for the answers. And surprisingly, they are all correct. Is it surprising or? But they are all correct. So, you can see, it is fused soda lime. Okay? Excess sodium hydroxide in presence of calcium oxide. So, you can see the whole of this. Okay? It is a carboxyl group. So, what does that mean? It means the carboxyl group is going to go away. Okay? And what shall we form thereafter? We shall form CH3, CH2, and finally CH3. Okay? And what is this? This is N-propane. That's brilliant. That's brilliant work. But now for this is the Waals reaction. What is it? The Waals reaction. And with this reaction, there is doubling, okay, of the carbon chain, where the sodium is going to take away this Cl, okay, and the CH3, CH2, it doubles, and we form CH3, and then CH2, okay, and everything doubles. So this is CH2, okay, and finally CH3. So basically it is as simple as this. And so how many carbon atoms? This is 1, this is 2, 3, 4. And what is 4? 4 is named as beauty. But it's an alkane, so we shall add ANE. and it becomes butane. So do you see how interesting this was? And so that's how the questions appear. However, in some questions they'll say complete and propose the possible mechanism. Write the possible mechanism. But now, no, these reactions, now the mechanisms are not. But in some reactions, they will just say complete, like how you see this, and then write the IUPAC name. Okay? For example, I can give you this CH3. See? Let me make science a bit fun. CH3 and then Cl, and I react it with Waals. CH3. Oh, no, this is Waals, sodium. This is sodium. Okay, so I react it with sodium in presence of dry ether, and then I do some heating. So what shall we form? And this is now just for fantasy and to make you understand the concept. And I just say complete the reaction and then propose and then write the IUPAC name. And this is my reaction. CH3, 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 Cl. Sodium in presence of dry ether. And some heat. And so what shall we form? Can somebody unmute and say the IUPAC name? And I should write something. You are still figuring it out? It's okay.
So is there a quad?
Quad?
Yes.
No, it's tetra.
It is 2,2,
Wait,
3,3 tetramethylbutane.
Wait, I write it. You're saying 2, 2.
3, 3.
3, 3. I hope you see how I'm writing. The letters are separated by commas and then hyphen.
Tetramethylbutane.
Tetra. Methyl. Methyl what?
Butane.
It is one word. Okay. So that's Dennis. Who else? Who else? Edwin, Anta. Sorry. Hey, you guys. Okay, Edwin. Let me write it here.
2, 2.
2, 2.
3, 3.
3, 3.
Tetramethylbutane.
Tetra. Okay, that's good. Tetra. Methyl. Butane. So it is written as one word. Okay, that's good. That is brilliant work. That is brilliant work. So you all
What
have
about
that.
5?
You all have the same. Eh? Which 5?
If there were 5 methyl groups.
It is penta. If there are 6 methyl groups, hexa. If there are 7, hepta, and so on. Okay?
Why isn't it buta?
I don't know. You can ask the IU pack. So basically, the nomenclature is okay. However, now for Anita's case, I don't know. She's quiet. I don't know. Is she still around? Okay, so this, yeah, your compound is okay. Even the nomenclature is okay. Let me write now. Everything that is this side is going to double.
I'm around but confused.
You're around but confused. It's okay. You speak. From where? We studied this reaction in our previous lesson, whereby we saw this as the Waals reaction, and we can use it to prepare alkanes. Okay, and with this reaction, we heat sodium in presence of dry ether. Okay, it doubles the carbon chain. It doubles the carbon chain, where everything, you can see where the halide, the halogen is, the chloride is. So you're going to take away the chloride and to be taken by the sodium. Okay, and everything this side doubles. So we can see, let's write our product. It is going to be CH3 and then C. Now we have the CH3 here. Okay, and then another CH3 here. Now since everything is doubling, so also it is going to double. So you have another C, then with this, the rest, it is doubling. So you write C and then CH3, okay, and then the CH. So this is going to be our product. And nomenclature, like I told you, sorry, we shall always name. It didn't stop. In the other lesson we had nomenclature from. No, it didn't stop from there. We shall always name. And so when you are naming, now which may be this, the key, the screen is going to be filled up with pens. So you have, this is going to be a carbon 1, this is going to be a carbon 2, okay, and this is going to be a carbon 3, and this is going to be our carbon 4. So this is our parent chain. The rest are groups that are attached on the parent chain. Okay, so therefore you have this group and you also have this group on carbon number 2. So we shall write 2 and then we put a comma and then we put another 2. Okay, we put a comma. Now since they are the same groups, okay, they are the same groups and these two are attached on carbon number 3, then we shall still go ahead and put 3 with a comma and then 3. Okay, and then we put a hyphen, and there are 4 methyl groups, so that one shall be tetra. 4 is named as tetra. Okay, tetra, and then tetra what? They are methyl groups, so you shall write methyl. Okay, so that becomes tetra methyl. Now what is the parent chain? It has 4 carbon atoms, and what is 4? 4 is bute, so that one becomes bute, tetramethyl bute. And which bute? Is it an alkane? Is it an alkane? It is an alkane. So alkanes are named by adding suffix n, and that's the IUPAC name of this product, and that's how simple it is. Is it okay to everyone? Yes. So basically that's how I'm going to erase everything on the screen, and we proceed to, I think, properties of Arcane. Now with the properties, here we see how Arcanes behave. And initially I was saying that Arcanes are generally unreactive, blah blah blah. So this is where we shall see why they are generally unreactive. Okay? So let's start with the physical properties. What are they? Are they solids? Are they gases? Are they liquids? Do they have high melting point? Do they have high boiling point? What are they? Okay? And how do they behave? So number one, the nature or the appearance, the nature, the lower alkanes, the ones with the ones from carbon 1 to carbon 3. Okay? I mean CH4, then CH3, and then CH3, and then propane. So these ones, they are the lower alkanes. They are generally gases at room temperature. Okay? Generally, they are gases at room temperature. In other words, lower alkanes are gases at room temperature. Now, why are they gases? Now, for you to become a gas, the forces of attraction between your molecules must be far away from each other. You remember senior 1 chemistry? Matter, even historians can do that. That draw particles to represent how particles are arranged in different states of matter. And then this is gas, and then liquid, kinda compact, okay, kinda close together, and solids really close together, compacted together. So because now, for it to exist as a gas, it means the forces of attraction between these molecules, the intermolecular forces of attraction, must be weak, that they can easily overcome. Is it overcome or overcome? I think it is overcome. That they can easily be overcome at room temperature. Okay? They are weak, that they are easily broken at room temperature. Okay? And so the molecules therefore become further apart from each other, and you exist as a gas. Is that okay? Yes. So that's why these lower alkanes, they are gases at room temperature, because their boiling points are very low. Very low. Okay? Less than 25, which is the room temperature, degrees Celsius. So once your boiling point is less than 25 degrees Celsius, then you will exist as a gas at room temperature. Now, the moderate ones, from carbon 4 to around carbon 8, carbon 9, they are liquids. Okay? Yeah, from 4 to around carbon 9. Even sometimes 4 can. Okay. So, but from carbon 4 to carbon 9, they are liquids at room temperature. Why? Because now, the intermolecular forces of attraction, okay, holding their molecules together. So if these are the molecules, okay, if these are the molecules, then the forces within molecules here, okay, the forces holding these molecules close together, they become a bit strong, that they will hold these molecules until when they turn into liquids. Not so? But higher alkanes, Now for these ones, they are going to exist as solids at room temperature. Now why are they solids? It is because now they are melting, they are boiling, their melting point, in fact, in this case, is higher than the room temperature. So they will exist as solids. Why this? Because of the intermolecular forces of attraction. Okay? Intermolecular forces of attraction are strong to keep these molecules close together, that even at room temperature they cannot be overcome. Is it okay? Now, in your mind, you should be asking yourself that what are these? What are these intermolecular forces of attraction? What are they? Which animals are called intermolecular forces of attraction? Okay, we shall see them. And in organic chemistry, we shall also study bonding, where we shall talk about them in details. And I made a video about bonding in organic, in compounds, and you can go and watch it and have fun. So basically that is their existence. So what can easily explain the existence is the boiling points. And so which factors do affect the boiling points? Before that, like I've said, what can easily explain this? It is the boiling point. Okay? The boiling stroke melting points. Now, what is boiling point? What is melting point? Now, the boiling point, boiling, so a substance boils if, I don't want to talk about the vapor pressure, but normal concept, normal science, basic science is when you reach the boiling point of a substance, then the substance will turn from a liquid, okay, to a gas. Now that is when you've attained a gas. Now for melting, when you reach the melting point of a substance is going to turn from a solid, okay, from a solid to a liquid, like melting ice. That is simple. Boiling water. Those are just simple concepts. So therefore, boiling or boiling point, it's a temperature at which sorry for that, a substance is going to turn from a liquid to a gas. And melting is a temperature at which, melting point is a temperature at which a substance is going to turn from a solid to a liquid. So for you to melt a solid, for instance ice, then you must apply heat that is going to break the intermolecular forces of attraction, holding these particles close together. Okay? You must apply heat that is going to break these intermolecular forces of attraction. So like I told you, this the solids are really strongly attracted to each other. Sorry, there was a network glitch. But yeah. So the solid particles are strongly attracted to each other. And so you need to heat them, okay, to overcome these intermolecular forces of attraction that are holding the solid molecules, solid particles close together, for them to become far apart from each other. Okay? And so when they become far apart from each other, then we shall say that your solid has melted. Okay? So that is melting. So this was initially a solid, and then this one, it is now a liquid. So now, let's talk about our alkanes. Now these alkanes, they are non-polar, okay, substances or molecules. Non-polar molecules. What does non-polar mean? They do not have any charges, okay? They don't have any charges within their molecules. And so what does that mean? Then the molecules, they do exist what we call the van der Waals forces of attraction. Now we shall study this in inorganic chemistry in details. However, I also made a video, it's there, okay? You can go and have a look at it and appreciate the van der Waals forces of attraction. It is there in our classroom. So they do exist, the van der Waals forces of attraction. Now these are forces of attraction that do exist within non-polar molecules. And now these forces of attraction, they are so weak, okay, compared to other forces of attraction such as hydrogen bonding, okay, hydrogen bonding. So molecules that do form the van der Waals forces of attraction, they are going to be very weak with very low melting and boiling points. Okay, so that's why alkanes, you can see, they do exist as gases at room temperature. But however, you can see that when you increase the carbon chain, are you seeing? Now the complexity increases. Now they are turning into liquids, but when you increase further, they turn into solids. So what does that tell you? It shows to you that these van der Waals forces of attraction, the more they get stronger. Should I repeat that? The more they get stronger, the more they become hard to be broken. Yes, in quotes. And so the more they become hard to be broken, then the higher the temperature, the higher the boiling point, and the higher the melting point. Okay? Yeah. The more they get stronger, the higher the heat that is required to break them. And so the higher the heat, then the higher the boiling point, and the higher the melting point. So you can see, if low alkanes exist as gases at room temperature, and higher alkanes, so the medium, they are liquids, and higher, they are solids. What does that show to you about these van der Waals forces of attraction? This is some guy who discovered them. So what does it show to you? It shows that as you increase the carbon chain, then the magnitude, the strength of these van der Waals forces of attraction increases. Okay? And so if the magnitude increases, then temperature required to overcome them also increases. Heat required, not temperature, to overcome them also increases. And so if heat increases, then these ones, the higher they will exist as solids, the medium they will exist as liquids, okay, and the lower ones will exist as gases. So we shall talk about more of van der Waals forces of attraction in inorganic chemistry as far as bonding is concerned. So however, these alkanes, they generally have lower boiling points and melting points compared to other organic compounds. Which compounds? Alcohols and carboxylic acids. If you compare an alcohol of the same carbon chain, maybe we can compare an alcohol, okay, with 2 carbon atoms and an alkane. okay, with 2 carbon atoms. So this is CH3, then this is CH2. We shall see that this is ethanol, sanitizer, the one you like taking. And this sanitizer exists as a liquid. Okay? But for ethane, we have seen it exists as a gas. So what does that imply to you? These alcohols, okay, they have high melting and boiling points compared to alkanes of the same carbon chain. Similarly with carboxylic acids, you can check. This is the carboxylic acid of the same carbon chain. Okay? You can have a look. So this one will have the highest boiling point followed by this, and this one will be the last. So what does that show to you? It shows that with alcohols and carboxylic acids, they have high melting and boiling points compared to alkanes. And the answer is simple. With these ones, the alcohols and the carboxylic acids and the alcohols, they form what we call hydrogen bonding, or they form hydrogen bonds. We shall study this one too, okay, and we shall illustrate what hydrogen bonds are. But there is a video, you can go there and watch it also, concerning bonding in inorganic chemistry class. Now with alkanes, these ones we have seen that they do form the van der Waals forces of attraction. Okay? Now the hydrogen bonding, the hydrogen bonds, they are too strong. This one, too strong. Okay? But for van der Waals forces of attraction, they are weak. And so therefore, if you compare alcohols and carboxylic acids of the same carbon chain, they relatively have high boiling points compared to their fellow alkanes. Okay? Yes. And we shall try to illustrate what hydrogen bonding is and what van der Waals forces of attraction is. So I hope we are finishing from here. So explanation: alkane molecules are held by weak van der Waals forces of attraction, while corresponding alcohols are held by relatively stronger hydrogen bonding, which cannot easily be overcome. So today we are going to stop here, and I hope to attend to your questions.